2, 1. So sketching functions. Another example for you. So this one is, again, a polynomial. So I have done one example with regards to a simpler polynomial, which was degree 3. So I'll put up a link up above there to that example. Now this one is actually of degree 4, so it is a little bit harder and more challenging. But let's take a look and see if we can follow the steps of sketching functions, you know, once you have taken kind of the first and second derivatives and studied that in calculus. So the goal is to try to sketch the function as accurately as you possibly can without actually utilizing any sketching tools. So no graphing calculators or anything like that. And the main reason for that is to reinforce what you have learned throughout functions and calculus and applying it into kind of just one complete package of sketching and actual functions. So let's get ourselves started. So the first thing that I like to do is to find the domain. Now, finding the domain of a function sometimes is challenging. It just depends how desperate and how complicated that function can be. Now, for polynomials, it's actually rather simple because polynomials are defined everywhere. So when we say what our domain is, well, x is actually going to be the entire real number line. So it's defined for all of x unless we have constraints on the left-hand side or the right-hand side, but we don't have any constraints on the domain here. So my first thing is, if I look at this, now it is a multiplication of two functions, it looks like, right? So we have a product. So this one is a quadratic and this one is a quadratic. So if I expanded it out, this would have been to degree number 4, and it's nothing else but just a polynomial. So that's step number 1. Now, step number 2, the next thing that I like to do with regards to these sketches is I always want to try to see if there are any vertical or horizontal asymptotes. Now, this only applies when you have kind of a denominator. So you have some kind of either a reciprocal function or you're dealing with irrational functions where there's things in the denominator to worry about. So that's going to be, and it's going to give you some vertical asymptotes. Now, horizontal asymptotes are more so when you are interested in what is happening as your function, so your x tends, so your input, your independent variable tends towards positive infinity, and what happens when your independent variable tends towards negative infinity, so at the extremes. So is it going to be approaching some horizontal asymptote, okay, as you keep going? Well, in this case, it will not. It's going to blow up on us. So if we substitute, for instance, okay, very large numbers into here, our function is of degree 4, so it looks like, okay, this is going to be blowing up on us, okay, in the positive direction. So it's going to go off into positive direction in this case. Now, on the negative side, so as you go on, again, since we're substituting and we have a degree 4 function, so if you expanded this, okay, your first leading term would have been, well, in this case, it would have been 3, okay, x to the 4. So that x to the 4, if you substitute negative numbers in it, it's always going to be positive. So it looks like in both instances, okay, this function is going to be blowing up to infinity. Now, it's going to be blowing up to infinity, okay, on the negative side and on the positive side. So do we have any horizontal asymptotes? No, it just blows up on us. Do we have any vertical asymptotes? No, because we don't have any denominators to kind of worry about, and it is purely a polynomial. So that's kind of step number 2 within here. Step number 3, what it asks us is, find any holes. So again, this actually goes back of you understanding, okay, holes and what they are, and those only can happen if you do have kind of a numerator and denominator which is canceling out at one particular point, and it creates a hole, okay, in the function. For polynomials, that will not happen I'm going to put up a link up above there for you with regards to holes, and it also talks maybe about vertical asymptotes as well. Okay, you can take a look at that if you wanted to. But for polynomial functions, we don't have to worry about. Okay, so check mark over here, so nothing to worry. Number 4, find x-axis crossings. Okay, so zeros of the function. Now this could be crossings or it could be touching, okay, along the x-axis. So what happens here? Well, this is a little bit annoying because we have to take our function and we have to set it to 0, and we have to see, you know, what's going to happen. So I'm going to copy this. I'm going to bring it down. So this is for our next step. And what we have to do is we have to set this equal to 0 and find out where our roots occur. Now, we can actually see, so from right here, so it looks like x, okay, is equal to -1 is going to be one of the roots, and then there's, you know, 2 of them because this is squared. So that's what we have there. And now for this, okay, right here, so this is a quadratic. This might not be as nice, so what I'm going to do is I'm just going to use the quadratic formula to find those other 2 roots, okay, from that one. So this is a perfect square, so that's easy to do, so that's -1 there. And this one, well, we're going to take a look and see. Welcome back. So we have these 2 answers. So I'm going to just kind of approximate them over here. And of course, if you want the full roots, you can, you know, take a look over here if you want a lot more accuracy, but I don't think we need to for sketching. So now what we have is we have, you know, 0 at -1 at 0.18 approximately, and then 1.82 approximately. The next step, what I like to do with these graphings is to be able to do this, is to create test points for myself so that I can see where the function is positive and where the function is negative. I just know the 0 at crossings, or maybe possibly, you know, touching, okay, at 0. So the next step that I'm going to do is going to actually start kind of graphing this out for myself to see in point by point and provide test points. So here's my x-axis, my y-axis, okay, so for the function. And what I have is, so approximately over here at, I guess, -1. So we have, that's from coming from right there. And then on the positive side, 0.18. So I guess this is going to be kind of squeezed out over here. If this is 1, maybe, and let me just put this as 2, maybe this is 3. We'll see if this is going to be sufficient as we keep going through the sketch, but for now I think it should be. So we have, you know, a crossing, we said, or a touch at -1 at 0.18, which is going to be somewhere over here, and then 1.8 approximately 2, so that's going to be somewhere over here. So that's what we have. Now, my tests are going to be on the left of -1. I actually already know what's happening there because that's exactly what I did over here, right? So as x approaches to -infinity, I know that this has blown up on the positive side. So if I would take a test point, let's say -2, and substitute it in here, what I'm going to get is something which is going to be positive. So, you know, I encourage you to try to see that for yourself as you punch it in. So you can take a test point, for example, -2, substitute it into this equation, and then find out. So I can already see that it is going to be positive on this side. So this function is going to lie above the x-axis, all right? So it's going to be positive on this side. So that's that. Now, what's going to happen over here in between -1 and 0.18? So again, I can take another test point. I like 0, right? Because working with 0 is always nice. So if I substitute 0 in here, let's say that's going to be 1 squared, so that's positive, and then 1. So it's going to be positive again So it looks like, so all the way on this side, it's also positive, which is telling me that this point right there, although that shouldn't surprise us because it's x plus 1 squared, so it's going to look very much like a quadratic near that point. So it looks like it's going to kind of, look like this. It's going to be, and notice the function is going to be positive in both. Now we'll come back to this and then check it with some other tests. Now, what's going to happen as I continue? So how about from here to here? So in between these points. So I can substitute 1 as my test point. And that would be, so positive 1, so that's 3 minus 6, so negative 3 plus the 1, so I guess it's negative, so that's negative and a positive. So it looks like it's going to be negative over here on this side. All right, so I'm putting that negative above there because it looks like it's going to cross through that 0.18 and it's going to come down. So that's going to happen there. And then on the opposite side of 1.8, so on this side, so again, you can punch 2 or 3 as a test point, but again, because we've already said that as x approaches infinity, it's positive, so it looks like over here, I mean, without me even checking anything, so it looks like this side is going to be positive, so the function is going to be above the x-axis. So it's above the x-axis, then again, it still stays above, then it falls through, so it becomes negative, and then it goes positive. So we kind of know where it will be lying. Now, once we complete this, so this gives us a nice kind of a viewpoint, we can go to the next step and then we can say, all right, let's try to find if there are any y axes crossing. Well, there's going to be only one because it is a function, right? So we can't have 2 because then it wouldn't be a function anymore. And now polynomials are very well behaved, so we're only going to have one value there. And that happens at x is equal to 0. Now, I guess I've already substituted x is equal to 0, but kind of very quickly, I'm going to get, so I'm going to do it on the side here. If you substitute x is equal to 0, you're going to get 1. So 1 squared times 1, which is just simply 1. All right, so by that substitution, for x is equal to 0, I have my y crossing, which happens, so I'm going to actually kind of do it a little bit higher, so I'll do it over here. So it looks like it's 1, so that means here's another point. So, again, as I'm looking through this, this is my function, it looks like it's going to hit there and then start coming down, most likely. That's my guess. That's what I will have. So this is going to be kind of like this. It's going to start coming down like this. Okay, so this is what I believe. It's going to look something like that. Well, we'll see as we keep sketching this along. Now, once we have that y-axis crossing, we can go to the next point. And the next point within here, so it's going to get a little bit trickier for us. We want to find the critical points. And that's where the derivative is equal to 0 or just doesn't exist. Now, the derivative for a polynomial, which isn't restricted in any way, it exists everywhere. So we just have to take the actual first derivative and then see where it's going to be equal to 0. Now, if you forgot about critical points, I'll put up a link up above there for you so you can go through that in a little bit more detail. Now, that first derivative is going to be annoying because of the fact that, my function isn't very nice. So let me just take this, I'm going to copy it, and we're going to take the first derivative. So I'll kind of put it down here. So we have to take the first derivative, but the first derivative of this, if I paste it back in here, I can expand this out and create a polynomial, but I'm going to just use the product rule. So product rule, so this is, I'm going to take this as one function multiplied by another function, really. So I'm just going to use the product rule for my derivative. So let me do that in fast forward fashion, and then I'm going to find out what that derivative is. I'm going to simplify it, and you can try it on your own as well. So here's the derivative. It was, a little bit of work, but I wanted to kind of massage it out and then factor things out so that it's a little bit easier for me. So what I notice here with the derivative, if I now want to find the critical point, so if I set this equal to 0, so if I try to set this equal to 0 in this way, I will find that, okay, so I'll have one critical point, so where the derivative is equal to 0 at x is equal to -1. Now notice at that particular point, so we've already kind of knew that this is going to happen to us. So this is at -1 over here, right? So that's right there. And we know that the slope was equal to 0. So it definitely confirms that, we have some kind of a, minimum. I mean, we can take the second derivative, which we will do, and we'll confirm that. But basically, because we know the function is above everywhere and the slope is equal to 0 at -1, so it looks like we have a local minimum down there. Now, let's take a look where else, things fall apart. So I need to find out what the roots are here. So this is, again, just quadratic formula. So let me punch it in and be back. Here are my two roots. So that's one. Then I have another one over here. So it looks like I have, 3 places where the slope is equal to 0. So those critical points over there, or values for here now. So -0.26. So -0.26. Okay, so right here. So it looks like, so right here, what would happen? So we have, okay, so just a little bit off of this. So right here, this is -0.26. So it looks like this is going to be tending, like this, and then turning back through that 1 over there, okay? Now we can find out exactly what this point is. So this point, this peak right here, by just substituting into our equation, right? So we can find that critical point right there exactly. So it looks like it's, going to be, somewhere along there. So I can do that. And then the other one, which is going to be at 1.26. So that's a little bit further. So it's somewhere over here. All right. Okay, and my assumption is this is going to be somewhere over there down. So let's find these two. Right, let's see how far this is going to go, and then how far up the other one is going to be approximately. Okay, so I'll be back to check that out. So here are the critical points here. So there you have it. So those are the missing ones. So it's 1.5 approximately and -9.18. So it's actually a little bit higher than I drew it out here. So it looks like, so this actually continues upwards a little bit further. But that's exactly why we can, make such a nice prediction on this sketch. So this will kind of continue on. So it's going to go upwards. It was 1, so it's going to go about halfway, and then it's going to come back. Okay, so that's this point right here. And then the other one looks like it really swings down quite a lot. So it goes down to -9.18. So this actually continues on, and just, you can, I'm just approximating, I guess, but this is, the -9 a little bit further. And now it's going to start swinging right back, okay, in here. So I'm going to be careful how I draw this, okay? So this is going to be swinging back like this. That's my, guess. Let's see if we can confirm these. So this is a local, okay? My guess is this is a local kind of max. I know that the slope is 0 there, all right? The other one is a local min, okay? And the one at -1 is a local min as well. Now, it might turn out that at least the bottom one, the one all the way at -9, that's actually going to be an absolute minimum there, right? Because it looks like the function just takes off and is positive beyond there. So my guess is going to be this. This is going to now start taking off in this direction. and this is going to start taking off in this direction, and that's how actually the function is going to look like. So that's pretty good, because now we also know these values exactly, right? So if we would be extending, we know exactly these points. Now it does look like we also have some inflection points within here. So coming from concave up to concave down, and then from concave, I guess, down to concave up. So we're going to be running into those as well. Okay, so here, okay, let's take a look. Those are my critical points. And now, so it says, you can certainly create test points in here. So you can have test points. So notice that's what it says next. To identify where the slopes are positive and negative, right? So where the derivative is positive and negative. Now we have, so if we were doing this, okay, we would have multiple areas to be watching out for this. So, we would have to, again, okay, I'm going to just change colors in here. So we would have to check right here. So we would have to check this area to the left. So we can check if the slope is actually negative, right? So we can check that. So substituting into our derivative, so right here. So if we substitute it in here, so let's say if we picked -2, what would we get? Well, -2, so that's going to be negative. And then that's going to be 4, so that's 12 minus, that's yep. So it will be actually negative, right? So within there, it looks like our slope is negative, and indeed that's the case, right? So the slope of that function as I drew it is negative. So that confirms that I was actually correct. Now the other part that we need, so we need to kind of keep going in here, so we would have to go from -1, what happens along this little path to our derivative? Is the derivative now all of a sudden positive? So we would have to, let's say if we would substitute -0.5 into our derivative, again, -0.5, that would be positive. Yep, okay, so it would be, you can just check, so it would be positive, so it is indeed positive there. Now my next kind of test point within here would be, so I would have to now check, so the last one, I have to go from here all the way down here, right? Because I'm checking the derivative test points. So this derivative test points is easier because you can substitute 0. So if you substituted 0 in here, you're going to get, that's positive, and then that's negative, so then it's negative. So on that stretch, okay, and indeed, looks like the slope is all negative, right? So in this direction. And then beyond, if you keep going, so on the right hand side we would want to see if the slope is positive on this side. And so if you substitute in there, you can take, for example, 2 as your test point, so you would get 2, so that's positive. 2, 4, that's 12, 2, yeah, so we would get a positive out there. So that confirms, actually, so far our graph is looking pretty good. Now, we probably won't really need anything further. I'm pretty confident in here, how it looks like. We have all the things. The only item is we might need inflection points. And those inflection points, they're going to be coming up, it looks like from concave up to concave down. So somewhere over here. And most likely, probably somewhere over here, my guess. Those are going to be your 2 switches from concave up to concave down and vice versa. All right, so well, in order to check that, so that is the next item that we would have to look at. So those are inflection points right here. So taking the second derivative and then doing the test points on that second derivative. And then that's pretty much exhaustive search on this. Now, this isn't, fun, because here is my derivative, so g prime. I'm going to copy this, bring it down, and now I want to be able to take, okay, so this is my g prime of x, so that's my derivative, but I want to know the second derivative. And the second derivative again, so let me just use the product rule and then simplify. And let's see what we get. Here's the second derivative, so it actually is not that bad. It kind of fell apart on us, so that's pretty good. So this 4 is kind of irrelevant, especially if we want to set it to 0 to find the inflection points. So let's take a look where that happens. So I just have to solve really this, okay, to see. So I'm going to do that. It should be kind of 2 roots that I'm going to get out of here. So if I set this whole thing to 0, so let me be back. So here they are. So this is really nice. So it's just 2 over 3, which is, I guess, 0.666 and negative 0.666. So those are these points right there. So that would have been, so this is negative 2/3. So it happens right there. And then, so it looks like this is, positive 2/3, so it's somewhere actually over here. So it looks like it changes some. Now again, I just sketched it, right? So that point is a little bit further down. So it's, somewhere over there as you go through. Because that -9 is actually way further down than I have it. It's not really to scale. And now you can find these points for yourself, right? Again, you can just substitute it into your second derivative and find exactly what the y value is. So you can find that inflection point exactly. Now, is it at an inflection point? That means it has to go from positive to negative. And this would mean that we would have to do, so once again, kind of a test points. So here is negative 2/3, here's positive 2/3. So on this side, so if we substitute, let's say -1 into this equation, so -1, that's 9 minus 4. So that's positive indeed, so it's concave up. So this is concave up over here. So concave up in between right here. So we can substitute 0 in here, so that's nice, 0, so that's going to be negative. So that's concave down. Right here, right? So down, up, and then the last one over, so if we substitute 1, again, it's up. So this goes concave up. So indeed, so we do have an inflection point going from here to here and another inflection point going from here to here. Now, this also is going to confirm for us, as we're kind of going through, that indeed, we can find now our maximum and minimums throughout. So were we correct or were we not? So to the left of the 2/3, so notice that -1, it's concave up. So indeed, that's a minimum, right? And it's a local minimum. At the other one, so, between the -2 over 3 and the 2 over 3 that you see there, so that is a local maximum because it's concave down there. And then the other one is concave up again. So that means it is a local minimum. Now, in fact, because the function now just skyrockets up, that is a absolute minimum. So this is amazing, right? To be able to do this. Now, that's the entire sketch. I mean, it's a lot of work. As you can see, the video is extremely long. But if you walked yourself through this and you can repeat these steps, I mean, you have quite the skills to be able to utilize first derivatives, second derivatives, understanding critical points, finding maximum minimums on your graphs, right? Understanding the slopes throughout, all the intersecting points, both on the y and the x. Okay, so this is quite a bit of information. Now, just to confirm it, let's take out decimals and see if this indeed is how it looks like. All right, so here I punched it into decimals, and that's your function right there. Notice this is exactly how it looks like, right? So we have, now the only thing is that the scale, right, that I used, okay, isn't really the greatest. And notice that negative, let's see all these points, right? So this was negative 1, 0, so that is true. So right here, the peak is negative 0.264 and 1.53. So that's what we had. Okay, so that's right there. That's what you see there on the green in the ordered pair. The other one, so the one at the bottom, was 1.2. So notice 26. That's indeed the case at negative 9.18. So that's what you have there. Let's see if the zero crossing, 0.184. So that's the zero crossing that we found. That's indeed true. You see that highlighted there in yellow on the left. The other zero crossing, so that would be this one, and indeed that's 1.816. So look how accurate we've made it. Like, we have all these points, right? We even have, okay, so throughout there we can see that there's an inflection point which happens here, so that we can graph it, and then there's, I guess, an inflection over here. So that was a 2, so it's going to be at 0.66 approximately. So it looks like it's kind of going to be somewhere over here. At that point, right? That's where that occurs. I mean, this is phenomenal, right? So, I mean, of course, putting it into decimals or any graphing tool, it's so much easier, but you don't really learn anything, especially when you're starting off in calculus or functions and you're sketching these things out. First thing, once you go through these processes, of course, in the future, you'll be graphing them, but at least you understand these concepts and where they come from. So that is neat because you can apply it, into research if you ever go that way, or if you, do any other studies, especially in applied sciences, from engineering, some of the maybe health sciences. Okay, so depending on what you're studying and what kind of research you might do, give yourself a pat on the back because that's a lot of work. Okay, so thumbs up. I hope that this was useful. So here are all your steps again that you can utilize to graph and go through any and sketch any function. So those are the 8 steps that I use, really 7. Okay, see you in a future video. Thanks for watching. Bye, everybody.